the feedback loop, you need to tell me whether it's positive or negative, and when you go home, you need to justify to yourself why is this a positive or negative feedback loop. Okay. You should also know if something is not a feedback loop, right? We already did those examples. Okay. So so let's say we have some kind of an infection. So we have a bacterial infection of some sort, for instance, and this infection leads, okay, to immune cells, right? So I'm going to, you don't need to know exactly which ones until we hit the immune system, which is our last chapter of the semester, but you'll see how this happens. So you have some infection, and typically what happens is you have your immune cells, okay? You have, let's say, you have your helper T cells, okay, that have had a sense of this infection, and what they do is they will bind and they stimulate, okay, B cells. You don't have to know exactly what these are just yet. The question is, what kind of feedback loop is this? If this is even a feedback loop or not, okay? So what happens is the helper T cells will stimulate the B cells. So what B cells do, they will secrete something called, so these will secrete antibodies. So I'm going to leave this alone. Okay. So what helper T cells do, this square or this rectangular box, what they do is once they're exposed to a particular infection, so you have your infection, okay? Once the infection hits these helper T cells, they will secrete a protein called interleukin, specifically interleukin 2, okay? But that doesn't matter. Again, they secrete an interleukin, and the interleukin will act on the helper T cell that secreted it, okay? And this will lead to more interleukin release, okay? And that will act on itself. More interleukin. First of all, this is a feedback. And let me specify, is this a feedback? Because if I don't specify, you can't answer this question. It'll be cannot be determined, right? Which pathway are you referring to? Hello? Is this a feedback?
No.
Is there any back here?
No.
No, this is not a feedback. It's not even feed forward. It's just a mechanism, right? It just goes to an endpoint. It's a linear mechanism. Is this a feedback?
Yes.
Look at the arrows. Is there any going backwards?
Yes.
Yes. So what kind of feedback is this? Interleukins make you release more interleukins. What kind of feedback? Positive. Okay, good. So this is making sense so far?
Yes.
Another example. Okay. So let's say we have from the, so another example too. So another example, so let's say we have, let's take the female reproductive system, okay? So we have a hormone called gonadotropin releasing hormone. You may have seen this before, you may not. Bless you. Gonadotropin releasing hormone, which stimulates the pituitary to release two hormones. It releases FSH, follicle stimulating hormone, and LH. You don't need to know any of these names right now. Follicle stimulating hormone, luteinizing hormone. So it releases these two. Follicle stimulating hormone, this is I think next to the pancreas, this is the hardest example. So, and again, this is all in females, okay, this is women. So in this example, follicle stimulating hormone does the following. So follicle stimulating hormone, it stimulates your follicles, right, in the ovary. So FSH will do the following. So it will act on the follicle. So this is your follicle. Okay, it acts on the follicle to do two things. FSH acts on the follicle and makes it secrete estrogen. Okay? And it's E. It's actually estrogens. It's actually 100 different estrogens that are released. I'm keeping it super simple for you, saying that it's just estrogen, E. Estrogens released. So what estrogen does, here's a very interesting phenomenon. What estrogen does, and this is definitely a hard question, estrogen will increase FSH receptor in the follicle. Okay? Think about it. When you increase receptors to a hormone, the effect of the hormone will increase or decrease? Increase. If you have more receptors, you have more response, right?
Yes.
You'll have a more profound response. $1,000,000 question. What kind of feedback is this? This is definitely feedback. There's no question about it being a feedback, right? This is a feedback for sure. Okay?
Yes.
What kind of think and answer? Scholars don't babble up the answer. Scholars think. This one needs thinking. Think and answer. So FSH receptors being stimulated by estrogen, right?
Yes.
So if you stimulate FSH receptors, one of the effects is FSH will make the follicle grow and secrete more estrogen, right? So estrogen stimulates FSH receptors. FSH receptors will stimulate estrogen, correct? Make more estrogen be secreted,
Yes.
correct? So this is a feedback for sure. Logically, you can tell it's a feedback. The question is it negative feedback? Is it positive feedback? Here's the interesting part. It's neither. Which one? And then dead silence. What? Only 3 people are thinking? Is it positive? Everybody has to say at least one word. Is it positive? Is it negative? Or is it neither? That's 3 people. The answer is it is positive feedback. It's a very tough positive feedback because estrogen, see, if estrogen directly stimulates more estrogen synthesis, right? That's a classic positive feedback, right? It's acting through a pathway. So it doesn't matter what the intermediates are. And Mark asked this question. And that's what reminded me that I should use this example. See how your questions, take my crazy head and make me want to give you better examples. So everybody say, all hail Mark. Because I would have asked this on the exam, and you would have sat there scratching your scalp till it bleeds. I'm giving it to you. Yes, this is a positive feedback. I don't care if you have 10,000 steps in the middle. If the response is the same as the stimulus, it is positive feedback, irrespective of how many steps you have in the middle. Are we clear?
Yes.
Should you memorize this pathway? Heck no, not yet. When we do reproductive system, absolutely yes. There's more steps to this than this. Okay? I will give you that, but I'm just getting your feet wet. Everybody okay with this example?
Yes.
Okay. Another $500,000 question. This estrogen, it's called unopposed estrogen. This is all I did for 8 years. So this estrogen, no, not secrete estrogen, study estrogen. So this estrogen stimulates LH. Question is, first of all, is this a feedback? Think hard. You start with the hypothalamus, then the pituitary, then the ovaries. Correct?
Yes.
Now from the ovaries, you're going back to the pituitary. Hint, is this a feedback? Yes. This looks like a linear pathway. It's not. It is actually a feedback because you're going back and acting on a different hormone. Are we clear?
Yes.
But it's the organs that matter, not the hormone. Do you understand?
Yes.
So, the ovary is feeding back, giving feedback to the pituitary. The pituitary got it started, I'm getting you started, you're giving me feedback, correct?
Yes.
Doesn't matter which of you, it's still feedback to me. Am I clear?
Yes.
So this is another example of positive feedback. Okay, so estrogen exerts two positive feedbacks in the female body. One is on the ovarian follicles locally, and one is a long distance positive feedback to the pituitary. This LH positive feedback is what causes you to ovulate. And this is gotten rid of by birth control pills. And we've just come up with the male birth control pill that does exactly the same thing on a daily level. Okay, it cuts off that LH surge, and when you cut off the LH surge, men do not make enough sperm. Does that make sense? And and they're saying it's temporary. I don't know how much of it is true, but the drug has been approved, so it should be coming to the market in another year or so. But anyway, female birth control pill, this is how it works. Are you seeing different forms of positive feedback here? Hello, good morning. I'm on my 9th hour of talking. If I'm not getting responses, I'm going to do what's bare minimum and go home. Okay, what does LH do? I always say that, right? And then I keep babbling. Everybody's going to lose respect for that warning. So what does LH do? LH stimulates the ovaries again, okay, to secrete progesterone. Progesterone, pro means supporting, like pro-life, progesterone, pro means supporting. Just means pregnancy, gestation, okay, progesterone. It's a hormone that promotes pregnancy, correct?
Yes.
And thank you, state of Florida, that injects their male sex convicts, fantas, with progesterone. This is their punishment. It's called chemical castration. When men get, and this is perfect evidence for evolution. When men get injected with progesterone, they have zero interest in sex. It completely wipes out their sex drive. Okay? Perfect timing. And it's Ethan. Tell him I'm in class talking about sex convicts. Tell him I'm using his example. So what does that tell you? What does that tell us? What does that tell you? That we are interconnected. Females and males are not that separate from each other. Are we clear?
Yes.
So man was not made in the image. Men and women have the same effects. A woman gets injected with progesterone, she has no interest in sex. This is why during pregnancy, later pregnancy, she has no interest in sex. And it's very protective, right? Because intercourse can seriously damage the placenta. Am I making sense?
Yes.
So nature makes sure that you're not interested in sex. So in fact, in rats, what happens, very interesting, that progesterone completely plugs the vagina with tissue. So even if a male wants to impregnate or have intercourse, you can't do anything. Okay? And that tissue has nerves. It hurts the woman. She bites the head off his head off. Okay? So pregnant females can get seriously violent. Okay? Because they're not interested in sex at all. And it's hormonal. Why is this important? Men should understand that this type of an effect is actually physical. It's not because they're crazy. Right? We hear this, right?
Yes.
Normal public, must be. PMS is completely hormonal. It's not psychological. What are you thinking? If I injected a male with progesterone at exactly 6 in the morning, they will show PMS by 11 a.m. Serious PMS by 11 a.m. Same symptoms, okay? And cramping in the prostate. You want to know what that feels like? Okay? It gives you a rough idea of what cramping feels like, okay? So, understand that men and women are equal in the eyes of nature, okay? So, men go through daily cycles, women go through monthly cycles. It's the only difference. We go through PMS at 3:30 in the morning when cortisol peaks. Women go through it for a longer period of time. That's the only difference. Are we clear? If anything, you should feel sorry for them. that they go through that. Because men aren't even, nature doesn't even trust men with being conscious when they go through PMS. Okay? Anyway, don't get me started on that, or all the men are going to go complain to the dean. So, progesterone, that's why male sex convicts get progesterone injections. And when women are nymphomaniacs, they get progesterone injections as part of their cure. Okay? Because they lose all interest in sex. Okay? And progesterone, that's what it does. Okay? In males and females. We're not that different. Okay? So, important. And women go through all kinds of mood swings during pregnancy. It's because the parasite inside of them, the fetus, is taking up all her calcium. Imagine sucking all your calcium out. Okay? Of course you're going to get depressed and angry and bipolar. That's normal. It's expected. It's not, psycho crazy, right? That's what you should expect. And knowledge is power, particularly for males. You should know what's happening in a woman who's pregnant. You should know what's happening in a woman who's going through menstrual cramps and menstrual cycles, right? Because that's when you can become a better practitioner, a better human being on top of that, correct? Sermon's over. So what does progesterone do? Progesterone will shut off LH. Progesterone shuts off FSH. And progesterone shuts off GnRH. No wonder you lose all your sex drive. It shuts everything off. Birth control does this too. Guess what birth control is? Progesterone extracted from donkey urine. So when you're taking birth control pills, one of my high school students kept taking his sister's birth control pills thinking it's mint, because it was mint flavored. What an idiot. and so be careful, okay? So keep it away from children. So progesterone will hit everything. Okay? First of all, is this a feedback?
Yes.
Yeah. What type of feedback?
Negative.
Classic negative feedback. Are we clear?
Yes.
And that's it. This chapter is over. And with that, everything interesting is over. So now, away from dirty talk, we're going into back to boring, which is cell membranes. So are the feedback mechanisms clear to you?
Yes.
I've given you every single example. The one on your exam has to be made up, and I'm going to make it up. Okay? All the human examples, I think, are gone. All right. So on to the next chapter. Are there any? So I give you 2 minutes to look at your notes and see if you have any questions that I can clarify. Okay? And we're right on time. So I'm going to close this out and open another lecture. Actually, no, I'm going to make this week 1, so I'm going to continue with this. Okay. Any questions on feedback mechanisms? On the exam, the feedback mechanisms will be very straightforward. I will not include, that's why I'm teaching all these, because I'm not going to ask all these. Are we clear? These tough ones where you're scratching your head, I'm not going to ask these. It's going to be I'm like, do you know feedback mechanisms or do you not? Okay, that's all it's going to be. So don't overthink. Don't overthink. Cell membranes. So we're going into cell biology now. You should have learned a lot of this in your bio class. So I'm gonna rocket speed through this. A lot of this you should have learned from your bio class. If you didn't, let me know. I will post my 102 videos on this. Okay? I wrote 102. I created that class, and I taught it several semesters. So I have videos from there. I hope. I will post those videos for you to watch if you want. But you should have learned all that there. But I'm going to review what's essential and go right into our physiology. Cell membranes are phospholipid bilayers. And they have evolved all the way from viruses all the way to humans. Okay, you see cell membranes in animal viruses. You definitely see cell membranes in bacteria. You see cell membranes in unicellular, multicellular, all kinds of organisms. You see cell membranes in humans. Okay, I don't want to say all the way to humans. That makes humans sound superior. We're not. Okay, we can't do half of what viruses can do. Right? So nobody's superior, nobody's inferior. Every organism is unique and we should appreciate what it has. So cell membranes are phospholipid bilayers. Bilayers, meaning you have two layers, correct? So phospholipids have a head, a phosphate head, and you have tails, fatty acid tails. So this is what it looks like. Okay? And the phosphate heads, okay, face the water. Phosphate heads face the water. So the hydrophilic portions, the phosphate heads, the polar portions, right? So this is the cytoplasm, okay? And this is the extracellular fluid, ECF, extracellular fluid, okay? And you've got your cytoplasm here. And I wrote them in blue because they are both water rich. They're both water rich, so the phosphate heads face, they arrange themselves that way. And the inner portion I'm highlighting in yellow because it's very fatty. It's very hydrophobic. This should not be news to you. Okay? So this is hydrophobic. So hydrophobic. Okay, sandwiched between two hydrophilic environments. Are we clear?
Yes.
Okay. So this makes all cell membranes. This makes all cell membranes very selectively permeable. Things can't go through cell membranes easily. Are we clear?
Yes.
There are millions of cell membranes in a cell. Okay? The one we're most interested in is the plasma membrane. Plasma membrane is the outermost cell membrane. Note that down. Plasma membrane, and that's what we're going to focus on. Plasma membrane is the outermost cell membrane. We have mitochondrial membranes, we have nuclear membranes, we have rough ER membranes, we have Golgi membranes, lysosome membranes. We have membranes everywhere. Are we clear?
Yes.
Those are all cell membranes. Plasma membrane is one example of it. Is this clear?
Yes.
Yes, you need to be this particular, okay, in my class and everywhere. You have to know what's accurately correct. So plasma membrane is the outermost cell membrane. All cell membranes can be described as fluid and mosaic. So what do these words mean? Fluid here means flexible. Flexible. Normally, fluid means something that flows, right? Water flows. Water is a fluid. You don't want the cell membrane to flow, right? That cannot be good, right? It's your protective wall, right? You don't want that to flow. Here, fluid refers to the flexibility of the membrane, okay?
Yes.
So fluidity means the membrane is flexible. What does flexible mean? All F's, okay? The membrane can fold. The membrane can fold, okay?
Yes.
Now, so the membrane needs to fold, okay, when you need certain circumstances, okay? When you need to increase surface area, the membrane needs to fold. When you have an insulin response, so when insulin needs to work, for example, so when insulin binds, insulin is a hormone that makes your cells pick up glucose, okay? So for insulin to work, the membrane must fold. Okay, the membrane must fold. Okay, the first discussion section for 103A, you're not doing this, but 103A is the first discussion is talking about how exercise increases the flexibility of muscle cell membranes. I gave them a research paper to read, and how exercise makes muscle membranes, particularly in obese individuals, makes muscle membranes less stiff, and therefore increases sensitivity to insulin. This is why obese diabetics, when they exercise, their sugar levels improve. Okay? And this is that mechanism. Okay? So, folding of the membrane is needed for many important activities of the cell. One example being insulin response. Okay? If the membrane is stiff, the insulin response is poor. Are we clear?
Yes.
If insulin response is poor, the cell is starving. It doesn't use glucose. And the glucose more importantly, stays back in blood, making your blood sugar higher. Okay?
Yes.
So in that individual, unfortunately, fat cells love to take up that blood sugar. So if muscle's not picking up the glucose, fat will. And when fat picks up glucose, what does it convert it to? Fat converts sugar to, fat cells convert sugar to what? Fat. So a person who doesn't move, who sits around all day, right, and has no physical activity and overeats carbohydrates, what's going to happen to their weight over time?
Gain.
A lot of weight.
That's why. Because fat cells are very happy to receive, and that's a hibernation mode that we inherited from bears. So fat cells are very happy to receive that glucose. So when you exercise, muscle cells dominate over fat cells. Fat cells starve. They break fat down. And you lose weight over time. Is this making sense?
Yes.
So do you see why exercise is important? If you're interested in that exercise paper, let me know and I'll post it. You don't have to do anything with it, just read it. Okay, it's a very nice paper. So back to fluidity. The membrane's ability to fold. If the membrane can fold really well, it is really fluid. If the membrane cannot fold, it's really solid and it's not able to fold. Do you see the two extremes?
Yes.
Okay. So how is membrane fluidity controlled? It's controlled by many things. This is an hour-and-a-half lecture on its own. I'm not going into this. I'm going to give you only what's relevant. So in our membranes, the amount of cholesterol, a waxy steroid, okay, is stored, okay, in the hydrophobic interior of plasma membranes, specifically the plasma membrane. Okay, most of the cholesterol gets stored there. Now I want everyone to do this exercise with me, and only humans can do this, by the way. Okay, so when I went to Monterey Bay and I saw the big whale exhibit, it was completely wrong because they put cartilage between all the whale fins. Whales don't have that. When does a whale bend its fin? Fold its fin? You can't do that, okay?
Yeah.
And I corrected them and they almost threw me out. But only humans can do this, by the way. Okay, everybody do this. Call me crazy. Okay, here we go. Okay, so, but you can do this, right? You have a variety of movements and you must appreciate how beautiful our nerves are directing our fingers to move, right? How many degrees of movement can you? Nobody's doing this. What the heck? Am I the only one with my deficient ATPs doing this? Come on, okay? You can do this, right? Now, take a pen. It could be an Apple pencil. Shove it in there. Now do the same motion. Good morning. Can you have the same motion with that?
No.
That's what cholesterol does. This is cholesterol.
Oh.
Do you see how cholesterol limits your movability of your
Yes.
phospholipids? If you limit that movability, what happens to your flexibility?
It decreases.
Decreases. So cholesterol decreases the flexibility of the membrane. Are we clear?
Yes.
Increases the rigidity and decreases the fluidity, and they're both saying the same thing, of the plasma membrane. Children in West Oakland, okay, children that grow in West Oakland. West Oakland is predominantly poor. As far as I know, they still don't have a proper grocery store. They don't get, I mean, they do now have farmers markets, but even those are too expensive for these people to afford. The parents are always working, 3 or 4 jobs, so they're never home. And there are 3 McDonald's in West Oakland alone. Okay, so guess where the kids are going to eat? That's right. And so they get very poor nutrition. No surprise, obesity is rampant there, right? And there's no education, right? Parents are not educated about this. Kids are not educated about this. The schools don't give a damn, right? So these kids are running around and they are obese. Children, when they're obese, this is what's going on. Their muscle membranes become more and more and more rigid, which means their insulin is less and less and less effective, which means they're always hungry, which means they're eating garbage all the time. Make sense? And it makes them actually even more hungry. Right?
Yeah.
Try this. When you eat flaming hot Cheetos, I love them. But flaming hot, I call them flavored styrofoam. But flaming hot Cheetos, in 15 minutes, I'm hungry again. 15 minutes, and it's all corn. It's supposed to not do that. I'm hungry again. Okay? Salad would never do that to me. Most likely, right? Corn gets digested very easily. And it ruins over time, it ruins your insulin signaling. So no matter what you eat, you're hungry again, right? So these kids are screwed, right? They get diabetes by an average age of 13. They become diabetic because your pancreas burns out, right?
Yes.
So look at how unequitable practices and, many ways, the Republican ignorance of poverty and problems that we have, okay, can affect an entire population,
Yes.
right? West Oakland is still this way, as far as I know, okay? So science plays a role in all this. So if you're just learning this as, oh, I need this for my exam, that's stupid, right? This will affect you during your lifetime, right? This will help you, modulate your kids' diets, right? This should. You will take parenting much more seriously. Am I making sense? Because with that diabetes comes blood pressure. These kids most likely will have a life of no more than 30 years. Okay, and if that doesn't make you feel bad, you should not be a nurse. You shouldn't be a human, actually. But this is Trump's America, so who knows? Important. These kinds of things make a difference. Plant cells don't have cholesterol. Okay? Which is why coconut oil, which is 60% saturated fat, is 0% cholesterol. Because coconut doesn't know how to make cholesterol. It doesn't need cholesterol. It has a cell wall. It doesn't need cholesterol. But animal products do. So when you eat meat, any kind of meat, morning, day, and night, this is what's going on. Explains the diabetes in Texas. Okay? Because most Texans have meat all 3 meals. And they do not have vegetables to supplement that meat. Okay? African tribes eat 10 times more meat than that. But they eat 100 times more vegetables and grains. That cleans the system. Right?
Yes.
And we call Africans tribal. Okay? You should see their diet and you should see their medicine. Puts us to shame. Cancer incidence is minimal in Africa. Okay? Because their food is amazing. Okay? So never dismiss any custom without looking into it properly. Okay? So when you eat a lot of meat and you supplement that with a lot of vegetables, that counteracts the effects of that meat. In fact, it enhances a lot of the beneficial aspects of the meat. Okay? And this is one of those things. Vegetable-based diets compounded with a lot of meat will help clear out the membrane cholesterol. It's been proven. Okay? It clears it out a lot better over long periods of time. So high cholesterol in your membranes is a diabetes risk. Make sense?
Yes.
Okay. So you understand how the membrane kind of functions, right? So it's like a floating thing. So watch my hands. This is what the membrane should look like, right?
Yes.
It shouldn't flow away. So it should be solid enough to stay in place,
Yes.
but it should be able to do this. So it's like this, right? And when insulin binds, it becomes like this, right? Giving you a very strong response. Everybody got this?
Yes.
Okay. Now, so that's fluid. That's the fluid portion of the membrane. What about the mosaic portion? Mosaic means tiled. Everybody seen kitchen tiles, bathroom tiles, tiles in a library, right? On the floor, hello, tiles? Yeah. So it's basically a pattern appearance, right? Appearance of a pattern. If you have a pattern on the floor, right, that's a tiled appearance. So what are we really talking about? All membranes, all cell membranes will have embedded in them membrane proteins. Membrane proteins. So membrane proteins are embedded in the membrane. So here, this is the membrane, right? Okay, you've got membrane proteins embedded like that. So that gives a tile-like appearance. Everyone knows what a tile is. So it gives a tile-like appearance. So this is fluid mosaic. So when you describe the membrane as fluid mosaic, it's fluid and it has proteins. Are we clear?
Yes.
Okay, so that's what the membrane looks like. Everybody clear about fluid mosaic?
Yes.
I will ask it. Okay, so you better know it, and it's important to understand the biology of the membrane. Okay, now membrane proteins are classified into two. So you've got two types of membrane proteins, and I'm going to go briefly into this. It's not that crucial, and this should have been done in 102. So I'm going to go briefly into this, but I'll just go into what's needed for us. So there are two types of membrane proteins. You've got integral membrane proteins, or IMPs, integral membrane proteins. Integral membrane proteins are crossing the membrane completely. They go through both sides of the membrane. So the way I drew it, are those integral membrane proteins? They go through both layers, correct? So they pass both layers. And the way to think about this, they connect the external environment and the internal environment of the cell. Think of it that way. They connect both.
Yes.
And the second type would be peripheral membrane proteins. Peripheral means on one side. They're only found on one side. So I'm going to say this very carefully. So they're loosely attached. What does that mean? Loosely attached. Okay? They can come off easily, is the point. Are we clear?
Yes.
So they're loosely attached to one side. So my high schoolers always would call this, I teach this in bio, so they would always call this IMPs and PIMPs, right? IMPs, PMPs, right? It's fine. But what distinguishes them as brilliant is one of them said to me, well, PIMPs need to be loose. I said, wow, okay, if that helps you. But the way to remember, peripheral membrane proteins need to be loose, and I'm going to tell you why. PMPs are part of signal transduction. They carry messages into the cell. Tell me, if you're a messenger, can you say, oh, I'm stuck here, I'm not going to be able to move? Can you be a messenger?
No.
No. You have to be able to move if you want to be a messenger, right?
Yes.
Now do you see why they're loosely attached?
Because they are messenger.
Mm-hmm. So they need to carry the message. When people smoke, okay, the cells in your trachea, right? The cells in your trachea are all tightly connected to each other, correct?
Yes.
You do not want them to be loose, or air is going to escape out through the trachea. You don't want that. So you want tight junctions between these cells, right? The cells are very tightly knit together, right?
Yes.
Now, tight junctions are made up of integral membrane proteins and peripheral membrane proteins. Are we clear?
Yes.
One of the peripheral membrane proteins, okay, will come loose very easily if the integral membrane protein pops. I don't have 4 hands, so you have to imagine this, okay? And if you do this with me, you'll understand it. It's an amazing mechanism. This is an integral membrane protein talking to each other, correct?
Mm-hmm.
Imagine my knuckle as the peripheral membrane protein. Are you with me?
Yes.
Yes? So when people don't smoke, it remains like this, nice and happy. When people start smoking, okay, the smoke will shock the cell. And I told you, anytime cells are shocked, what shape do they take? They become circular. Good. When they become circular, they snap. Yes? when these snap, this knuckle of a protein comes loose. Okay?
Yes.
It will go into the nucleus and immediately tells the cell to start dividing. Because you have a hole in your neck. You don't want air to escape, right? You want to fill that hole, right? It's an injury. It's a response to injury. And when you keep on injuring something, and you will learn this in my cancer class if you take it in the summer, shameless advertisement, I'm offering it. The first lesson you will learn, the first time somebody was able to replicate cancer was by taking a razor blade and wounding rabbit ears. Now rabbits don't have any nerve in their ears, so they don't feel the hurt. But the guy kept wounding it, and within 3 months, got a benign cancer of the ear. So wounding, he was the first one in 1910 to discover that wounding causes cancer. Imagine the same wounding inside your body because you're eating extra hot Cheetos. That sets all the inflammation going. Hello, cancer. Make sense? Because you're constantly dividing. But do you see the looseness of that protein? If this protein were not loose, will the cell get the message of the injury?
No.
No, it's very, very important. Are we clear?
Yes.
If you're interested, that protein is called beta-catenin. Beta-catenin. It's a junction protein when you're healthy, and it becomes a transcription factor when you're injured. Okay, and beta-catenin is elevated in more than 75% of cancers, human cancers. So it's a very important protein. Do you see the importance of looseness of peripheral membrane proteins?
Yes.
Okay. I stood up, I'm done with exercise for the century. So I'm going to sit back. So use your hands. Okay, use your hands to learn this material. It's amazing how much you can learn with your hands. Okay. So peripheral membrane proteins and integral membrane proteins are together. PMPs can be attached to one side, or the example I gave you right now, they can be attached to an IMP. In fact, majority of times, they're attached to IMPs. So when the IMP gets activated, it kicks the PMP to the inside of the cell. Are you with me?
Yes.
So here's my IMP PMP signal transduction dance. Okay? So if this is my hormone, right? Okay, I don't have a hormone. Here's my receptor, and the receptor is literally shaped like this. I'm not kidding. So this is the integral membrane protein, right? And this is the tail of the integral membrane protein. It's actually called a snake receptor because it's shaped like that. And we're going to be looking into those in the middle of the semester. So this receives the hormone. It's called the head of the snake, and this is the tail. Attached to the tail, I want you to imagine, is a ball. Are you imagining the ball?
Yes.
Yeah. Even better, let's say that my leg is the tail, right? And I have a soccer ball attached to my leg. It's not glued, but it's there. It's sitting there, right? This is literally what happens, and the guy won the Nobel Prize for this. When the hormone binds, right?
Yes.
This thing starts dancing. Okay, the guy showed it under the microscope, not kidding. And when you start dancing, what do? One of the steps is you kick the ball. But you will not kick the ball unless you're dancing. You will not dance unless the hormone's here. Do you see this process?
Yes.
This is an example of signal transduction. Getting the signal inside. The hormone can't go inside, but the hormone can make the peripheral membrane protein go inside. And now the cell knows the hormone's here. All hell evolution. Isn't this amazing?
Yes.
And bacteria do this. So if you think you're advanced, bacteria do this. They have these receptors. Okay? So, what is my point? Peripheral membrane proteins can be attached to integral membrane proteins, right? And in fact, they are most of the time to get signal transduction going. Everybody see these two examples. My beta-catenin example for smoking and the hormone transduction, right? Getting the message across, getting the signal going. Okay, and when the whole thing is over, the ball comes back to my foot. Are we clear?
Yes.
And when the ball doesn't come back to my foot, most of the time you end up with cancer. It's a problem. Every step of this is a problem, right? If it doesn't work properly. Okay?
Yes.
So if I receive the hormone and I just sit there, what's going to happen? The hormone's not going to have an effect, right? But if the receptor is going on dancing without the hormone, right? Then you have an inappropriate effect, right?
Yes.
So anything that goes wrong in a pathway can result in problems. Again, that's what we're going to look at throughout the course, right? We're going to be looking at all these pathways. But peripheral membrane proteins are loosely attached because they serve the purpose of signal transduction. Let me write that out. Signal transduction. Transduct means carry through. Okay? Carry through. Trans means across. Carries the message across. Okay?
Yes.
So what do integral membrane proteins do? So peripheral membrane proteins are involved in signal transduction. They're part of cell junctions. Okay? They're part of cell-cell junctions. And very rarely they're enzymes. Okay? So those are their functions. Okay? What do integral membrane proteins do? A lot of things. They're very versatile. First of all, they stabilize the membrane. They're weight-bearing walls. Meaning, if I removed integral membrane proteins, what would happen to your membrane? If I removed weight-bearing walls, what would happen to your house? It's going to collapse. So integral membrane proteins were removed, the membrane will collapse. Are we clear?
Yes.
Okay, they're walls. They hold the membrane up. They hold the membrane up. Okay, so they stabilize the membrane. So why am I using bougie language? Because when I write like the Queen of England. Okay? When I talk all get up. But when I write, I become very bougie. Okay? So, and that's how tests are written. You think the MCLEX is going to use ghetto language? No. It's going to be scientific, right? So you need to be exposed to the scientific language. So I'm purposely writing my notes in a scientific way. But I'm explaining it in simple language. But you've got to get up to the technical writing level of your language, okay? So stabilize the membrane. So what does stabilize mean? They hold up the membrane. Now, what else do they do? They can also be enzymes. I'm gonna not go into that a lot. Enzymes are cellular taskmasters. You must have covered them in bio. They're also part of cell-cell junctions, okay? Huge part of cell-cell junctions. Okay. Extremely important, they are involved in molecular transport mechanisms. Molecular transport mechanisms. Okay? And how are they involved? They're involved as channels, carriers. Okay? So they're involved as channels and carriers. So these proteins help transport things, okay, into and out of cells. I'll give you an illustration. So if this is your membrane again, this is your membrane. I told you the middle portion is completely hydrophobic, right?
Yes.
Which means ions cannot go through this. Ions are water soluble. They're not going to be able to go through fat. Do you agree?
Yes.
So if you need ions to go through into the cell or ions to come out of the cell, they're both important. Ions need to go through the cell, into the cell, and ions need to come out of the cell. You need a special bridge. I mean, can your car wade through the ocean to go to the bay? No, you need a bridge, right? Same story, okay? You need a protein path to wade through. So I'm going to draw this in a really big way because I want you to see and appreciate the structure. So if you need a protein pathway, right? So if this is writing with the highlighter again. Okay, so if you have a very big protein that looks like this, right? Is this integral or peripheral? Integral, goes through both layers, right? It's integral. Think about it. It's surrounded by fat in the middle, correct?
Yes.
Okay, so what will all the water-soluble amino acids do? They will come away from the fat. They don't like the fat, right? They're hydrophilic. They hate the fat. So I'll indicate that in blue. So all the hydrophilic amino acids will orient to the middle, correct? Away from the fat. Do you agree?
Yes.
This forms a hydrophilic tunnel through which ions can easily move. Right? The fat is on the outside, right? So imagine fat on the outside, and I have an inner core. My inner core is hydrophilic because it stays away from the fat, and that helps you transport hydrophilic substances easily. Are you seeing this important fact? So all protein transporters have a hydrophilic core. Write this down. All proteins, okay, protein transporters have an inner hydrophilic core, and I call it the tunnel, okay, through which you can transport things. Now, if you don't have a tunnel, you can't transport, right? You need a special tube for things to go through. Do you agree?
Yes.
Now, proteins are not guaranteed to have a tunnel, but these transporters do, because that's what they do. They transport, so they have a tunnel. I'm going to give you a minute to see if that's sunk in. So hydrophilic, hydrophobic, you should be familiar with that. Hydrophilic means loves water. Hydrophobic means hates water. Okay?
Yes.
So if you're surrounded by water haters, all the water lovers are going to hide together, correct?
Yes.
And that's really beneficial because you have water-soluble substances that can easily then transport through. Any questions on this so far? Okay. Some of the other functions, IMPs act like immune billboards. You learned this again the last weeks of class, what these are. So they act like a billboard. What does a billboard do? It displays an ad, right?
Yes.
And you read the ad and you like it or you don't like it, whatever. So what these billboards do is they randomly select proteins inside the cell and they post them. Now, if this is a protein that is self, it's you, the immune cell will read that, right?
Yes.
And it'll move away. It's not going to react because it's self. And if it does react, despite it being self, you're in trouble, correct? Autoimmune diseases. Okay? Most of the time it won't, it'll walk off. But if you display a weird protein, correct, on the surface, then the immune cell is going to read that and go, uh-oh, this looks foreign, right? And then it'll initiate an immune attack on the cell. Are we clear? This is how we fight pathogens. Making sense? So those proteins are IMPs, the billboards. You want the billboard to be stable, right? You don't want it to be loose. Everybody get that?
Yes.
So those are the functions of IMPs. Any questions on IMPs? PMPs? Everyone okay? All right. So we're now focusing on cell transport mechanisms. Cell transport mechanisms. I want you to, so I'm going to shut up for 5 minutes and I'm going to draw something on the page. I want you to copy it as is into your notebook. And I want you to physically copy it, okay? So you need to write this out, okay, to learn. So here we go. Everybody should be writing. Because if you don't learn this, bye-bye the rest of the semester, okay? You need to know this. This is very, very important, okay? And this never gets taught properly, unless you've had me for 102. This never gets taught properly, so I'm definitely going over this, because I'm going to be using this left, right, and center in every single chapter. So you need to know this, very foundational, okay? All I want you to do is copy, okay? I'm not asking you to understand this at all. If you do, that's great, but just copy, okay? And then I'll explain it. So just copy for now. Draw this out as a chart, and nobody cares if it looks ugly in your notebook because you didn't plan the space. No one cares, okay? Just go home and redraw it nicely if you want. But the classification is important. Go ahead. Better? Okay. I'm blocking it?
Yeah.
Better? Well, no dignified way out of that one. Actually, we step out so that way you guys can see it. Okay, so now I want to explain this, at least one side of this and a little bit about bulk transport. So everybody understands what cell transport means, right? Substances are either going into the cell, that's called influx, or going out of the cell called efflux. E means exiting, right? Exiting flux. Flux means diffusion, really. So influx or efflux. Influx means movement into the cell. Efflux means getting out of the cell. Right? Everybody understands that materials are going in and out of cells all the time, right? They have to, right? Cells need nutrition, right? Cells need waste to be cleared. So you're constantly either taking things out of the cell or taking things into the cell, and this is happening all the time. Does everybody understand this basic fact? Okay? All right. So when that's happening, there are two main classifications here. If you're taking a few molecules at a time, right? 20 molecules at a time, 200 molecules, or even 2,000 molecules at a time, right? That's considered molecular transport, right? When there's a limit on how many molecules can go in, think about it. Is there a limit on how many cars can go through the San Mateo Bridge at any given time? Yes, that's why you have a traffic jam. Or you wouldn't have any traffic jam during rush hour. Do you agree? Of course there's a limit. Proteins are even worse because what happens is each channel is extremely specific. So protein transporters that transport sodium cannot transport potassium. Are we clear?
Yes.
Okay? So each and every ion has its own dedicated protein, right? When that's happening, you're going to hit maximum very, very fast. Are we clear? This is why protein transporters exhibit a phenomenon called Tmax. T stands for transport maximum, right? There's only so much that can go through at any given time. Is that point making sense?
Yes.
Whereas simple diffusion, I'll give you an example. If I have a big canister of oxygen, right? And I open the gas tank, it's going to out, right?
Yes.
And it'll keep on going until the tank is empty. Do you understand what I'm saying?
Yes.
There is no plateauing, right? It'll keep on going and then it's dead. That's it, right? So simple diffusion is like that. There is no saturability, right? As long as you have a difference, the molecules keep on moving. Okay? Osmosis is an example. Osmosis is simple diffusion of water. I would write that down for next week's lab. Osmosis is simple diffusion of water. Simple means, do you have proteins helping you? No. Simple means no proteins needed. Look at my diagram here. What does it say? Here, no IMPs, right?
Yes.
Yes, no IMPs. Okay, so that would be simple diffusion, which means the molecules wade right through the membrane on their own. They don't need any help, right? Remember, the middle of the membrane is hydrophilic or hydrophobic? The middle of the membrane, hydrophobic, right? So only fatty things go right through. Am I making sense? So what things go through by simple diffusion? You need to know this. Those would be, okay, so let me use a different color. Choosing color takes forever. Okay. Let's let's say this orange, okay? So oxygen goes through by simple diffusion because it's non-polar, okay? Carbon dioxide, thank heavens, right? Because when you breathe in the lungs, the last thing you want is protein transporters, right? It's going to slow everything down. So we evolved to make sure that oxygen and carbon dioxide can easily pass. You must have wondered, why didn't we choose any other gas? Why did we choose oxygen and carbon dioxide? Because they go through simple diffusion very easily. They're the right size and they facilitate our respiration very easily. Are we clear? The last thing you want is putting a barrier or a bureaucracy like a protein in the middle, right? We don't want that. So oxygen and carbon dioxide. Water, surprisingly, but water is very slow because it's polar. This is why osmosis is slow. So when somebody drinks absolutely pure water, it takes them, depending on the amount, it takes them anywhere from an hour to hour and a half to die, right? Because osmosis is slow. You never drink absolutely pure water, you know that, right? Because it's a poison. Hello?
Yes.
Yeah, you never do that. You never drink absolutely pure distilled water because it is a poison. It will get into your cells and make your cells explode, right? So you don't want that. So water movement is very slow, thank heavens, right? So if you're water poisoned, you could be cured. You could be brought back, to your normal state. So water movement is slow because it's polar. Urea moves this way. Okay, and urea is your main waste. Okay, urea moves by simple diffusion. Urea also moves by channels. Water also moves by channels. Okay, but it also moves by simple diffusion. It's very, very slow. Are we clear?
Yes.
And this becomes very important in the kidney, particularly. And the last thing to move through by simple diffusion are your steroids. That's why you never, ever mess with steroids. How many of you have applied cortisone on your skin to get rid of rashes? Okay? I have measured my blood sugar because I have sensors, right? So anytime I get bitten and I've applied cortisone, okay, my sugar jumps anywhere from 160 to 320 units when I apply cortisone. I'm not surprised. That's what cortisone is supposed to do. Cortisone is a glucocorticoid. What does gluco mean? Glucose. It's supposed to increase glucose. Diabetics should go nowhere near cortisone. Okay? Because it will spike your sugar. So what happens in non-diabetics? When you're really stressed out, okay, your cortisol levels spike. So you can imagine what your blood sugar looks like when you're stressed. Okay? Make sense? So the importance of remaining calm, right? Forget that A. Be calm. Right? Those are the changes that are happening. It's important to know. Steroids absorb through your membranes very, very easily. Am I making sense? There was an instance where in my lab I was packing estrogen pellets for my breast cancer experiments. So I take estrogen, put them into plastic pellets, and we would subcutaneously, surgically implant them under the skin of mice and rats, right? And what was amazing was we had 14 women in the lab. I was the only guy, and I was in front of a fume hood, right? So the fume hood always did this, right? All 14 of them started cycling at the same exact time the next month, and then they stopped cycling for the next 3 months, and their estrogen levels were off the roof. I was doing, I'm not kidding you, 10 to the negative 12 gram of estrogen. That's 1 followed by 12 zeros. 1 over. That much estrogen. Teeny, tiny amount of estrogen, right? What happened? Estrogen spread through the air. It absorbed through their skin enough to muck up their cycles. So when they all got checked, our lab was shut down for 6 months. It was nobody's fault, it's not my fault. And I had to get checked for estrogen like 10, 12 times that year. I was completely normal. And then it made sense. The fume hood pushed the estrogen away from me. It protected me. Nothing happened to me. Right? And that's when I discovered that 99% of my sperm are Y, and that I could never ever have daughters. So I cried a lot about that, because we're all boys in the family. I wanted girls, so that never happened. So anyway, the bottom line is hormones have all kinds of effects. Don't take them lightly, okay? And they can absorb through your membranes like no tomorrow. And I visually saw that, okay? These women stopped cycling because the brain thought they were pregnant, because this estrogen absorbed right through. And I told you, what does estrogen do? That can stimulate LH. And LH leads you into a sense of pregnancy, right? Because LH stimulates progesterone. And they lost all interest in sex, they were not cycling, and everybody thought, mentally, their brain physiologically thought they were pregnant. Never mess with steroids. Never. Okay, that was a huge lesson learned. Okay? Never mess with steroids. They can have a tremendous effect. So when you put that stupid cortisone, might as well put aloe. Aloe is a lot safer, right? Yes, it takes a little while and it's not as effective as cortisone, but cortisone is put there to suppress your immune cells. But cortisone has a million other effects that you don't know about, and it gets absorbed into your bloodstream extremely efficiently because steroids cross the membranes. Do you see? One little word in one little chart has life-changing circumstances, life-changing consequences. Never judge anything as stupid. Make sense?
Yes.
Okay. So steroids cross the membrane very easily. Okay. And when you take facilitated diffusion, now one more point about simple diffusion that will be on your exam. Ions can't go through because ions are polar. They're hydrophilic. They cannot wade through fat. Am I making sense? They get repelled by fat.
Yes.
Thank heavens. So ions don't go through. Okay. So simple diffusion can only, I would write this down, simple diffusion can only follow a chemical gradient. It cannot follow an electrical gradient because ions can't go through. Simple. I will write that out for you. So chemical gradients only, and everybody knows what a gradient is? A difference. Gradient means a difference. If you don't understand a word, it's your job to raise your hand and ask me that question. If you just sit there and just pretend like you know it, you're not learning. There are concepts coming that's going to depend on this. So if you don't understand, stop me. And you don't have to be polite. Stop me and say, what the hell is a gradient? I'll tell you what that means. Okay? So chemical gradient means difference. Difference in amounts. High to low. That's a gradient, right? Low to high, that's a gradient. So chemical gradients only. Okay? Not electrical gradients. So electrical gradients cannot drive simple diffusion. Are we clear?
Yes.
Because ions can't move. It's a very simple concept explained or stated in a very bougie way. Okay? If you think about it, it's actually really simple. Facilitated diffusion evolved mainly to transport ions. So tell me, will it follow chemical gradients only, electrical gradients only, or both chemical and electrical gradients?
Both.
Both. They can follow everything. Make sense? So facilitated is perfect, but what's the problem with facilitated? Only few of these can go in at a time, because if too many ions went in at a time, you will electrocute the cell. Do you see how evolution happens for a reason? So any organism where ions went in bulk probably died. Make sense? And they were weeded out. So you want channels to only send in a few ions at a time. Okay? Not more than that. Okay? Because you will end up electrocuting the cell. You don't want to do that. Okay? So facilitated diffusion transports ions and polar substances like amino acids and glucose. Okay? So what things get through? That would be things like glucose. Okay, I'm going to draw a line here. Okay? Glucose, amino acids, so sugars, amino acids, anything that's polar, right? And ions. Everybody okay with facilitated diffusion? There are two types of facilitated diffusion. Okay? Of course, life can't be that easy. So there are two types of facilitated diffusion. Okay? And I'm going to do this as a separate chart because there's a reason. I'll tell you why in a minute. But I'm going to do it as a separate chart, okay? So, protein transporters so these are applicable to both facilitated diffusion and active transport. That's why I'm doing it as a separate chart, because they apply to both. So protein transporters can be classified into two broad categories, okay? So you can be a carrier or you can be a channel. Guys, the word carrier, watch my hand, carrier, right?
Yes.
Versus channel. Are you getting the gist of this? Okay. Channel is me, not wanting to move. A carrier is you, a lot of energy and wanting to run around. Not by the looks of this class right now, but sure, during normal times. So what is the main difference? The main difference is this. Carriers literally move the material. Okay, and I'll demonstrate this. I have a little dance for this. Carriers, conformational change is required. Guys, 70% of your exam is going to come from this table, the first lecture exam. So if you think this is dense, it is dense. You're not wrong at all. So what should your realistic expectation be? I didn't learn anything from this in this hour and a half. Totally fine with me. Okay? In fact, that is what it is. I'm teaching you so much material here. Right? This is a whole chapter in a book that you're learning right now. So what should you do? Don't look at this tonight. Yes? Look at this tomorrow when you have your study time. And look at it very calmly and carefully. Know all the definitions first. And then explain this to yourself once or twice. And you've mastered it. I promise you, you'll have mastered it. And when you go to Pearson, right, it has some amazing animations on each of these. If you don't want to do Pearson, go to YouTube and watch the animations of each of these. But watch animations, it's very helpful. Okay?
Yes.
All right, so conformation change is required. Channel, minimum conformation change. Minimum to none. Okay? Conformation change. Okay? They can both be facilitated diffusion. Okay? Facilitated diffusion can involve carriers and channels. They can both be employed. So what is my carrier channel dance? Okay. So channel is very easy, right?
Yes.
So I'm a channel. I have to be an integral membrane protein, correct? Any protein transporter, you have to go through the membrane or things aren't going through, right? So I'm a full-on integral membrane protein, right?
Yes.
And I have a lid on my head, right? So let's say I'm a glucose channel, I have a lid on my head. So what does insulin signal transduction eventually do? It'll add a phosphate to my arm and moves my lid away. Now what can happen? Glucose is high in blood, low in cells. Glucose is always low in cells because cells use glucose, right?
Yes.
So glucose should flow through. Am I making sense?
Yes.
And only glucose. I will not let anything else through because remember, I'm specific. I'm a glucose channel, so glucose channels go through. Diabetes happens because people don't have enough glucose channels. That is the reason for diabetes. Okay, for most kinds of diabetes. Okay, particularly type 2. Okay, the channels are not there. Okay, so that's how these channels work. Is this minimum shape change?
Yeah.
Yeah. Now compare this to a glucose channel in the intestine. Okay, it's a very different channel I'm talking about. So it's a special glucose channel in the intestine. And what it does is it grabs glucose, moves it here, right? And then back again, grabs glucose, moves it here, grabs glucose, moves it here, right? And you might think, well, wouldn't you need energy for this? That looks like you would need energy. No, you don't. Okay? Trust me, you don't. Because it's facilitated diffusion, right? But I'm carrying the glucose versus I'm just sitting there. You go wherever you want. Do you see that subtle difference?
Yes.
So for channels, I don't need to change my shape too much. Just open my lid, right? Open my gate. Those are channels. Okay? What does a carrier do? It physically moves the damn thing. Okay? But my shape change physically moves the molecule. So there's a huge shape change happening with me for a carrier, but minimum shape change happening for a channel. Everybody got that?
Yes.
Now, I repeat again, facilitated diffusion can be channels and carriers. They can both do facilitated diffusion. But active transport is only carriers. No channel can do active transport. I will ask this. And you will need to know this throughout the semester. You can never have a channel for an active transport mechanism. Never. Okay? It is physically impossible. There are very few things that I am very sure about, and this is one of them. Because the function, it doesn't make any sense. You're using energy for active transport. You're going to have to move the damn thing. Clear?
Yes.
There's no question about it, right? The principle doesn't allow you to do it, right? Now, protein transporters, okay, when you look at carriers, carriers are classified into two. Why should your life be any easier? So carriers are classified into two. So you've got two of these. One of them is a uniport mechanism. Uniport, uni means
One.
One.
Singular.
one. Or you have a co-transport mechanism. And co-transport usually refers to two.
They can transport one way or the other way.
Yeah, we're getting into that. The table's not over. Keep dreaming. Table's not over. There's more classification coming. Co-transport means two substances. Okay? There are protein channels that are protein carriers that can transport four substances at once. Okay? But thankfully we don't need to know those. So co-transport is two molecules, usually. For our purposes, two molecules. Okay? Uniport is one molecule, one way. You will use every word from this chart in every lecture till I die. We're going to use these terms. So believe me, this is foundational. So one molecule, one direction. Co-transport is classified into two based on the direction. So if you can have a symport or an antiport, and this should already tell you, right? Sim means same direction. It used to be called cisport, and they didn't like the way it sounded, so they changed it to symport. So a symport, I'm going to draw this for you, okay? You have two substances, okay, going in the same direction. Are we clear?
Yes.
Okay, and an antiport will be easy to draw, right? One is going in one direction, another is going in the other direction. In this course, you're going to see several examples of each one of these. Okay, so I'm not giving you examples right now. You're going to learn them all through the semester. Okay, and uniport, okay, is one substance, one direction. Any questions on that? This is all molecular transport. Okay? Meaning you're transporting few molecules at once. Right? Always zoom out and see if it fits with the bigger picture. Are you with me?
Yes.
Okay. So look at this. Look at the chart in your notebook. Because if I zoom out, it's going to look really tiny. So look at the chart in your notes and tell me if there's anything there I can clarify. Yeah.
What do you mean by conformation?
Conformation means shape. The protein has to change shape. So if you look at this, right? If you look at me, right? I'm carrying the substance across. Is my body shape changing? Yes. If I were a channel, I'm just like this, right? I'm just doing this. Very minimum change. Whereas this is a massive change, right?
Yes.
So conformation change, the protein has to change shape. The entire protein changes shape. right? Minimum conformation change, only one part of the protein has to change. Very minimum, yeah. What else? Yes,
So channels are never active, always passive.
thank you, absolutely,
Carriers can be both.
yes. And this is the type of studying you have to do. Okay? Again, I recommend that you don't study this tonight. Okay, do it tomorrow. Let your brain organize this information.
So in facilitated fusion, why don't carriers need ATP?
They do if you're pushing things up the hill. When you do active transport, which we haven't covered yet, right? But you're doing facilitated diffusion, right? Facilitated diffusion, you're going down the gradient, right? High to low. When you're rolling down a hill, do you need energy? No, in fact, you give out energy. Make sense? So understand that when substances go down the gradient, meaning you're going high to low, you give off energy. When you go the opposite, low to high, you have to use energy. Yes?
Yes.
So that's going to make a difference in a minute. Yeah.
For simple diffusion, why is it that ions are unable to pass through, but water is?
The middle hydrophobic layer.
Right.
Ions are extremely polar. Water is only slightly polar. It's the degree of polarity. Anything else? Yes.
For the second transaminated protein transporters, how does that fit in with the previous method? Is it just
Protein transporters can be facilitated diffusion, or where am I going to put that in the chart? Right? It has to be separate. Right?
Okay.
Yeah, but that's where it fits.
Thank you.
Mhm. Good questions. Anything else? So everyone knows I have office hours at 8, correct? On Zoom. And the tutor has office hours for you once a week on Wednesday. Okay? 5 p.m. Okay? Wednesday, 5 p.m. on Zoom. Okay? So you can connect to him through there. You can also go to the tutoring center. He'll be sitting there tutoring other students. So you can go reach him, or you can talk to other A&P tutors in the tutoring center if he's not available. Okay? But all this tutoring is free for you, right? So utilize it. So I'm going to introduce you to active transport, and then you can go home because we only have 5 minutes. So I'm not going to explain all this to you. We'll do the explanation next Tuesday. Primary and secondary active transport. Primary is a constitutive mechanism. I told you what constitutive means. Constitutive.
It's always on.
It's the opposite of on and off, right? It's either always on or always off. Okay? Whereas regulated means on and off, on and off. You go through cycles of that, right? You're able to turn it on and you're able to turn it off. Okay? Constitutive means you can't. You can't change it, right? It's either permanently on or permanently off. Clear?
Yes.
Okay. So primary active transport is always on. Now, if anybody asked me to define life, right? Define life, okay? I would say it's my primary active transport. Because if my primary active transport has stopped working, I've been dead for an hour. Everybody see this?
Yes.
And there's a reason why I'm being so dramatic. Because it is that important. 70% of your calories goes into primary active transport in the body. 70%. That is not a joke. Okay? So this mechanism is extremely important. Primary active transport is it's an all-in-one protein, okay? And it is working all the time. All the time. Secondary active transport is found only in very special locations. For example, it's found in parts of the kidney. It's found in parts of your intestine. That's it. Are we clear? Yes. Secondary active transport is not found everywhere. Is this making sense?
Yes.
Primary is found everywhere in the body. Every single place. It's ubiquitous. If you're alive, you have primary active transport. End of story. Okay? So, secondary is a very special mode of evolution, right? Secondary evolved from primary, and secondary depends on primary. Look at the names. Primary means most important, right? Secondary means second in command, right? I listen to the primary, correct?
Yes.
It's like that, right? So secondary active transport depends on primary active transport for it to function. And that explains why nobody likes unsalted chips. Have you had unsalted potato chips? They're disgusting. I'd rather die, okay, than eat those. I had the misfortune to eat lightly salted. Oh my God, it was so just garbage, right? I'd rather not eat anything. So when we do secondary active transport, I'll be able to explain to you why salty foods are so yummy. Okay? Why people have such a strong, if you give caramel chocolate versus salted caramel, and you somehow feel like the salty enhances the sweet, it does. There's a physiological mechanism for that also. But why would you want potatoes to have salt in it? Raw potatoes don't, they're disgusting. Yes? If you ate raw potatoes, okay, you'll actually benefit from them. Okay? They're not going to give you almost any calories. Am I making sense?
Yes.
You need, when you put because the starch you eat gets excreted, you won't absorb any of it. Salt is needed to absorb all those carbs. Now do you see why your doctor wants you to give up salt in your food? Salt contributes to obesity way more than sugar ever will, because salt is the reason sugar gets absorbed. This is also why people can get bored of sweet things. If I gave you 20 sweet bars and you ate those 20 sweet bars, you're going to be like, enough. I'm not eating any more of this today. I'm done. Right? The brain gets saturated.
Yes.
Nobody says that about salt. Who has said, I don't want salt anymore? Nobody does. Because salt is essential for nutrient absorption. Are we clear?
Yes.
Everything piggybacks on salt, and that mechanism is secondary active transport. Pure and simple. I told you my stories have a point. Long point, but I get there. Right? So, very important. So if you want to lose weight, cut your salt. It works. Cut your salt down. Okay? Slowly, but cut your salt down. Okay? It will help. You will absorb sugars less. Primary active transport is what we call a pump. Pump. So when I say the word pump, it only refers to primary active transport. Are we clear?
Yes.
Secondary is not a pump. Okay? Secondary is secondary active transport. That's it. It's a carrier. That's it. It's not a pump. Because what does a pump do? When I plug the electricity in, it should be able to use that energy, correct?
Yes.
Secondary does not. Secondary does not directly utilize energy from ATP. Are we clear? Only primary does.
Yes.
And primary needs to work for secondary to work. Make sense? Primary needs to work for secondary to work. So I highly recommend you watch YouTube animation on this before you come Tuesday. That will be the first thing we'll do Tuesday. I'll finish bulk transport. We'll wrap this up in another half an hour, and then we will move on to action potentials next week, okay? Action potentials, that's our main topic on Tuesday, okay?
Yes.
Have a wonderful weekend. Bring questions to me if you have them. Email me questions if you have them. Or I'll see you at office hours, okay?
Okay.